Okay, so let's continue for our revision chapter of thermodynamic of gases. So let's just start with question number 1. Okay, so this is question number 1. A container is filled with a nitrogen dioxide at the pressure of 110 Pascal. The initial volume is 4 times 10 to the power of 3 meter cube, and the initial temperature is 410 Kelvin. The gas undergoes the following steps. So heated at constant pressure to P, so this one is P1, and I can know that my P2 is actually 610 Kelvin. So for the second process, cold at a constant volume to 305 Kelvin, and for the third process, cold at a constant pressure to 116 K. So this is this one should be temperature. So so cold at constant pressure to 160 K, and finally heated at constant volume to 410 K. So from here, from this 4 process, I can see that the temperature of all of 4 of the process is keep changing. It means that there's no isothermal process included in this process. So for the first question, so show that the above steps in PV graph. So I have my PV graph. So this is my P and this will be my V. So for the first steps, heated at constant pressure. So my pressure for the initial pressure is 1. Let me just draw down bits. So this will be my 110. So this is Pascal and this is meter cube, of course. So let me just drag it down. Heated at constant pressure to 610 K. So this one should be my initial volume. So so this one should be 4, and I believe this one should be the volume of all whether it changed to anywhere, the volume should be times 10 to the power negative 3 meter cube. So this one is 4, and this will be my first process. And heated at a constant volume to 610 K. So I assume here should be my 610 K. So this will be my second volume, and we will calculate later. So this will be my first line, which is the constant pressure. So cold at the volume. And cold at a constant volume to 305 Kelvin. So let me just observe for a moment. Cold to the, so I believe this one should be pointing downwards. So we will calculate the value later. So this one should be my second process, and cold at a constant pressure to 160 K. So this will be my third process, and finally heat at the constant volume to 410 K. So this will be my fourth process. So this is A, and this is B, and this is C, and this is D. Alright, so let's just calculate for the volume V2, which is here. So what will be our V2? Okay, so this is the constant pressure. So constant pressure, what we can use one of the three gas laws, which is P is directly proportional to T. So this will be our formula that need to be applied, which is Charles' law. And this is PT, P1 T1 equals to P2 T2. So my initial pressure should be 110, and my initial temperature is 410, and the pressure for the second, okay, this will be our unknown. Oops. Sorry, I have, this is a mistake. Suppose the pressure should be the constant. This is because the process undergo expansion at the constant pressure. So the constant pressure, the pressure is the constant. I'm sorry. So let us think about another formula. So which is T is directly proportional to V. So sorry. So our formula is V1 over T1 is equal to V2 over T2. Okay, so this is the variables that varies. So my initial pressure is 4 times 10 to the power negative 3, and my initial temperature is 410, and my V2 is this one. And what will be my T2? So my T2 is this one, 610 K. So what will be my V2? 4 times 10 to the power of negative 3. So 410 times 610. So the V2 will be 4.951 times 10 to the power negative 3. So this is 4.951 times 10 to the power negative 3, of course. So this is the first process. So let's just move on to the second process, which is the condition of constant volume. So my T3 supposed to be, oops, this one is 3. So my T3 is this one, 305 Kelvin. So since the condition is the constant pressure volume, so what we need to use, the formula that we need to use is the formula that does not consist of volume. So we can know that P is directly proportional to T. So okay, so P1 over T1 is equal to P2 over T2. Okay, so what will be my pressure? Okay, so my pressure at initial state should be 110, since the process is from B to C in the second process. So my initial pressure should be 110. So what will be my initial temperature? So my initial temperature should be the temperature at point B. So okay, so my initial temperature becomes 610. So my pressure P2, which is the unknown variable. So my T2, my T3, this one should be T3, and T3 is what we need to find. So P2 is 610 times 305. So what we get is the 55 Pascal. So I can conclude here is the 55 Pascal. Okay, so yeah, we have done for all the values that we need to find. So alright, so this is how we answer for the graph. So let's just move on to question B. Oops. Okay. So calculate the work done by the gas. So we know that the work done is actually the area under the graph. So I can see that from this graph. Okay. So this is a square graph. So from here, our work done is actually area under the graph. So our work done, net work done, is actually this one. So what I can do is use this big area subtracted with the small area, which is okay. So the area of the big surface area, which is 110. So 110 is the length times the 5.95 times 10 to the power negative 3 minus 4 times 10 to the power negative 3 minus the 55. So the big rectangle minus the small rectangle. So this is the same, minus 4 times 10 to the power negative 3. Okay, so what will be our answer? Oops. So, okay. Almost done. So my final answer will be 0.107 joule. So this is the net work done. Okay. So this is the net work done of the gas, which is moved from A, B, C, and finally D. And not the process does not stop at D, and it eventually back returns to point A. So this will be my net work done, which is 0.107. Okay, so calculate the heat. This one should be net. There's a word missing here. So calculate the net work done flowing into the gas. Okay, so based on first law of thermodynamics, Q is actually equals to increase in internal energy plus the work done by the gas. Okay, so we can see that the gas is the initial state of the gas is actually at point A. Point sorry. So the initial state of the gas is actually at point A. So so we can see that after undergo some process, which is from A, B, C, D, and finally return to A, we can see that the temperature of the gas after the for process, the temperature of the gas does not change. The temperature of the gas is constant. So the change in temperature is actually 0, which is the gas finally returns to its initial state. So the change in temperature is 0, and hence I can conclude that my internal energy is also 0. So hence my Q is actually equals to my total net work done. So my net heat flow is actually equals to my net work done, which is 0.107 joule. So this will be our net heat flow of the gas after undergoing the for process. Okay, so we have done for question 1. So let's just go through for question 2. Okay, let me just erase all this one. Okay, so let me zoom in. Okay, that will be our number 2. So a gas in cylinder is cooled and compressed at constant pressure. So this is constant pressure of 3.50 times 10 to the power of 5 Pascal. So the volume is reduced from V1 1.5 times 10 to the power of 3. Okay, sorry, not times 10 to the power of 3. Should be 1.50 meter cube to 0.60 meter cube. So this will be our V2. So okay, reduce its mean compression. So in this process is removed from the gas. There's a word missing. This is the heat. 3.60 times 10 to the power of 5 joule. So this is negative, which the Q is actually leaving the system. So calculate the work done by the gas. Okay. So alright, so the work done by the gas is actually, so since the condition is the constant pressure, or we can say that is isobaric process. So isobaric process, which is constant pressure. So I can say that my work done is actually equals to the pressure, which is constant, times the change in volume. So my pressure is 3.50 times 10 to the power 5, and my change in volume is 0.60 minus 1.50. So 0.60 minus 1.50. So this will be So this will be negative 3.150 times 10 to the power of 5 joule. So we can see that the work done is actually negative. So it means that this work done is actually work done on the gas, since the process is the isobaric compression process. So work done is actually negative. So the change in internal energy. So what will be our change in internal energy? Okay, so we have first law of thermodynamics. So this is increase in internal energy. So since the system is decompression, so what we have for work done is actually negative work done. So our Q is negative 3.60 times 10 to the power of 5, and this is the one that we need to find, and this will be 3.150 times 10 to the power of 5 joule. Okay, and so 3.60 times 10 to the power of 5 plus 3.150 times 10 to the power of 5. So the final answer is 4.50 times 10 to the power of 4 joule. So this will be our final answer. Okay, so that is how we find the change in internal energy in the compression system. So we have done for number 2. So let's just go through for number 3. Okay, let me just scroll it down. Okay. A cylinder with frictionless piston contains. Okay, so this will be our volume, which is the initial volume, 1.04 times 10 to the power negative 3 meter cube. So of 1 mole of an ideal gas, so this is mole at the pressure, so our initial pressure is 1.01 times 10 to the power 6 Pascal. So the gas undergo adiabatic expansion to 2 times of its initial volume, original volume. Okay, so my V2, I can say that is actually 2 times of its initial volume, which is 2V1, which is 1.04 times 10 to the power of negative 3 meter, okay, never mind, meter cube. Okay, so, and finally undergoes isothermal compression back to its original volume. Okay, so calculate the lowest pressure attained. So what will be my lowest pressure? Okay, so finally undergoes isothermal compression. Okay, so what will be our. Alright, so this is for the first process is adiabatic expansion. So for the second process is isothermal compression. So what we have for our lowest pressure is okay, let me just simply draw my graph. So this is my PV graph, and this will be my first point. So what we have here is actually the adiabatic expansion. So this will be our second point. So for the second process, isothermal process, so which is less steeper than the adiabatic curve. So what we have is here. So the pressure is not necessarily returns to its original pressure. So Let me just draw it more accurate. So this is adiabatic, and this will be my isothermal process. Isothermal adiabatic. Okay, so this is first one, and this will be my second one. Okay, so calculate the lowest pressure attained. So I believe the lowest pressure is actually mean this point. So let me just use another color. So my lowest pressure is actually here. Okay, so this is related to the first process. Alright, so what will be the formula that is applicable for adiabatic process? So what we have here is actually P1, V1, and V2. So basically the formula that we can use is P1, V1 to the power of gamma is equal to P2, V2 to the power of gamma. Okay, so what will be our gamma? 1 mole of an ideal gas. So, okay. The problem is the question only mentioned about ideal gas, so let me just check about it. So if I'm not mistaken, if the question mentioned about the ideal gas, basically it means about the monoatomic gas, if I'm not mistaken. So let me check for a moment here. So what will be our okay. So is the question mentioned about diatomic gas because the question the book shows here is the gamma constant for diatomic gas. So let me just refer back to the question. Is there anything I missed? Okay. So oh, okay. I basically missed something. So the question given here is actually gamma is actually equals to 1.40. So 1.40 basically is the diatomic gas. Okay, so I missed this constant. So okay, let's move on. So what will be our P1? 1.01 times 10 to the power of 6. So my V1 is 1.04 times 10 to the power negative 3. So to the power of 1.40. So equals to my P2. So my P2 is the variable that need to be found. So my V2 basically is 2 times 1.04 times 10 to the power negative 3. So what will be my P2? 6 1.04 times 10 to the power negative 3 to the power of 1.40. So 2 times 1.04 times 10 to the power of negative 3. Oh, here I missed something, which is gamma to the power of 1.40. So my final answer is 3.827 1, 2, 3, 4, 5 times 10 to the power of 5. This is Pascal. So this will be my lowest pressure, which obtained from after undergoing the first process. So there's something need to be noted, which is this one. So let me use another color. So this is the utmost important thing that we need to remember, which is the adiabatic process. The equation for adiabatic process is quite different from our normal gas law equation. So this we need to be careful in case we have done wrong. So this will be question A. And let's just move on to question B. So calculate the lowest temperature attained. So what will be our lowest temperature? So we know that okay, let me just think about it. Okay, lowest temperature, and so what we have is actually the P1 T1 1 minus gamma. If I'm not mistaken, is it 1 minus gamma? Even for me, also forgetful. Oh, okay. So, alright, so the formula is actually wrong. So we know that based on the normal gas law equation, so P is actually inversely proportional to, okay, let me check again for the formula. Okay, alright. So is it initial temperature given? Okay, so since the initial temperature is not given, so we cannot use the, okay, so I wonder this one should be what formula which is applicable. So let me just observe about it. Okay. So is there any initial temperature given here? Okay, no. Alright, so let me just no. Nope. Isothermal compression back to original volume. So I can know that the temperature here and here is actually the same. So my initial pressure, my lowest pressure, temperature, sorry. So my lowest temperature here should be which one? I wonder. Okay. This is quite confusing. So the N is given. Okay, so since the mole is given, so what we can do is actually PV equals to nRT. So from here I can know that the, okay, let me just check about it. Okay, so based on the gas law, okay, So based on the gas law, which is the Gay-Lussac's law, it's quite confusing. So P is actually directly proportional to T. So what we have here for the lowest temperature, so since here is the lowest pressure, so as well as the temperature, the lowest temperature located at here. So what we have is the pressure. So our pressure is 3.827 times 10 to the power 5. So my V basically is, my V2 is, 2 times 1.04 times 10 to the power negative 3. So equals to 8.31, and this will be my unknown. So my T will be 2 times 1.04 times 10 to the power negative 3. So divided by 1, 8.31. So the final temperature we have is actually 96. Not 96. Should be 95.8 Kelvin. So based on Gay-Lussac's law, so just now I have forgotten the Gay-Lussac's law, which states that the pressure is directly proportional to T. So it's okay. So let's just move on to the third question, which is part C. So C basically is this graph. So let me just draw it more clearly. So this is my P and this is my V. And what we have here is the point A, and this is adiabatic curve, and this is B, and this will be my isothermal curve. So this one is, just like that. Okay, so my initial pressure, what we have is 1.01. So is it all the pressure are times 10 to the power of 6? No, so this one should be the 5. So what I need to do is just write down times 10 to the power of 6. So this is Pascal, of course, and this is meter cube. And this one, no, not this one. So this point B here, which is the lowest pressure. So the lowest pressure that we get is 3.827 times 10 to the power of 5. Okay, so what will be our V2? So my V2 is actually 2 times 1.04 times 10 to the power negative 3. So this will be my 2.08 times 10 to the power negative 3. So what will be our initial temperature? And the initial temperature will be 1.04 times 10 to the power negative 3. So this is how we draw the graph of adiabatic changes and isothermal change. So okay. So if we wish to prove whether the point C will return to its original state or not, so we just find it out what is the pressure for point C. Okay, so we know that T is, this is the isothermal process, so basically T will be my constant, so which is 95.8 Kelvin. Okay, so my V is 1.04 times 10 to the power of 3. So this is meter cube, and so this is pressure, and V is equal to nRT. So my N is 8.31, and my T is 95.8, since it is constant temperature. So what will be my V? And my V is 1.04 times 10 to the power of negative 3. So this will be my P. So 8.31, 95.8 divided by 1.04 times 10 to the power of negative 3. So basically is my pressure is 7.655 times 10 to the power of 5. So this is Pascal. So basically we can see that the C which located at here is between this one and this one. So we prove that the final pressure at point C does not return to its original pressure. Okay, so we have done for question number 3. I think okay. So let's just erase all this one. So basically this is how we understand the concept and do it one by one. So all the three gas laws, which is the Boyle's law, Charles' law, and Gay-Lussac's law, is quite important, and is also sometimes it's also can be our reference to determine all the adiabatic equation, which is quite similar to all the gas equation, but the difference is only in terms of that ratio, which is Cp to Cv, which is this one. So we need to memorize and understand the concept. Okay, so we have done for question number 3. So let's just move on to question number 4. So this is A and this is part 1. Define the molar heat capacity at constant volume of an ideal gas. So molar heat capacity is molar heat capacity at constant volume. So basically it's defined as the heat required to raise the temperature of 1 mole of gas by 1 K at constant volume. So this is how we define the molar heat capacity at constant volume. Okay, so using the first law of thermodynamics and the ideal gas, so I wonder whether you can see it. Okay, so show that CPM is equal to CVM plus R. Okay, so this derivation is quite long, so let me just erase all this one. Okay, so this is part B. Is it part B? Not part B, is part A still with part 2. So what we need, the equation that we need is actually this one. Okay, so So let's just begin with the molar heat capacity at constant volume. Heat capacity at constant V. So based on first law of thermodynamics, so Q is actually increase in internal energy plus the work done by the gas. Okay, so since the volume does not change, so our work done basically is 0. Since there is no change in displacement, so there's no work done and there's no work is done by the gas. So basically our Q is equals to our internal energy of the gas. So what we have for internal energy of the gas is actually N CVM delta T. Okay, so based on the definition, so molar heat capacity at constant volume, which is the heat required to raise the temperature of 1 mole of gas by 1 K. So what I can do is sub all this as 1. So what I get for final internal energy is basically is CVM. So this is the molar heat capacity at constant volume for 1 mole of gas, which raised by 1 Kelvin in terms of temperature. Okay, so this is the first information that we need. So let's just go through for molar heat capacity at constant pressure. Capacity at constant pressure. So our Q is N CPM delta T. So since we raise the temperature of 1 mole of gas by 1 K, so the temperature is actually 1. So this is 1 and 1 mole as well. So what we get is CPM. So this is Q. So this is the molar heat capacity of 1 mole of gas at constant pressure, which raised by 1 Kelvin, of course. So based on the first law of thermodynamics, so this will be our second information. So Q is actually equals to increase in internal energy plus the work done. So remember, this first law of thermodynamics we use at the condition of constant pressure, which is this one. Okay, so what we have here, my Q is CPM. So as I said that from the previous video, since both cases we use is the 1 mole of the gas and the temperature is raised by 1 Kelvin. So at constant pressure and constant volume, so both cases are the same. So I can conclude that my internal energy for the ideal gas is basically equals to CVM. Okay, so this is the reason why we can substitute the internal energy of the ideal gas at constant pressure, which is equal to our CVM. So this will be our P delta V. So P is the constant and the one that changes is actually the volume. Okay, so let's just continue. So PV is actually equals to NR delta T. So T temperature is still changes, and this will be 1 and this will be 1. Mole will be 1 and the temperature also will be 1. So what we get is R. So this is CPM. So this is the final conclusion that we made, which is CPM is equal to CVM plus R. Alright, so that is how we derive the formula of CPM is equal to CVM plus R. Okay, so we have done for number 4A part 2. Alright, so let's just move on to B. So let me just write here. Okay, so this is my B. Describe the change in thermodynamics quantity. So this is thermodynamic quantities of an adiabatic compression according to the first law of thermodynamics. So according to the first law of thermodynamics, which is internal energy plus the work done. Okay, so this is adiabatic compression. So since my Q is 0 for adiabatic process, which the heat does not enter or leaving the system, so this will be my 0, and this will be my internal energy. So since the process is the compression process, so the work done is actually on the gas. So I can conclude that my change in work done is equals to my increase in internal energy. So this will be my first quantity, which is 0 joule. So my work done is negative, which the work is done on the gas. So as the work is done on the gas, so I can conclude that the internal energy increases since the internal energy is positive. So this is the statement that we need to state so that we are able to define the quantity of all the values that contains in the first law of thermodynamics. So we have shown that the Q is actually 0 joule, and my change in work done is actually negative value, and my change in internal energy is actually equals to positive value. So this is how we state the quantity of thermodynamics, first law of thermodynamics in terms of adiabatic compression. Okay, so we have done for question part B. So let's just move on to part C. So what will be our part C here? So a gas with gamma 1.40. So this 1.40 show us that the degree of freedom. Okay, so let me just explain it. So our ratio of Cp over Cv is actually F plus 2 over F. So if my gas is actually diatomic gas, so which is 5.2 over 5, so 7 over 5, basically I get 1.40. So this 1.40 is came from came from this formula, which is 5 plus 2 over 5. So this 1.40 means that the gas is actually diatomic gas. Okay, so if we wish to find other ratio which is monoatomic gas or polyatomic gas, what we can do is actually substitute this degree of freedom, which have different type of degree of freedom for monoatomic gas, diatomic gas, and polyatomic gas. So if we wish to find monoatomic gas, we just sub the degree of freedom of 3 into here. So what we can get is actually the constant or the gamma constant for monoatomic gas. So basically this one is aimed for the diatomic gas. Okay, so let me just erase this one. Okay, so this is gamma, okay, initially at the temperature of, so 30 plus 273 is basically 303 K. So the volume is 3.50 times 10 to the power negative 3 meter cube, and the pressure is 1.013 times 10 to the power 5 Pascal. Undergo an adiabatic compression. Okay, so this is adiabatic compression to 1/3 of its in original volume. So my V2 is basically equals to my 1/3 V1. So assuming the gas behave as an ideal gas, so state the type of molecule used. So as I mentioned just now, since the gamma is 1.40 from the formula that we use, so basically the gas we use is actually diatomic gas. Okay, so calculate the final pressure of the gas. So final pressure, so since it is the adiabatic process, so what we need to use is the adiabatic equation. So state the final pressure of the gas. Final pressure, okay, so let me just, alright, so what we can use is actually this one. Gamma is equals to P2 V2 gamma. Okay, so since V2 is the 1/3 of V1, so this will be my gamma. Okay, so this is P1 V1 gamma. Alright, so this one is gamma V1 to the power of gamma, so P1 V1 gamma. Okay, so this one can be cancelled, and P1, what will be our P1? 1.013 times 10 to the power 5, so is equal to P2. P2 is the one that we need to find, so 1.40. So finally our P2 is our P2 basically is 4.716 times 10 to the power of 5. Is it power of 5? Yeah, it is power of 5. So this is the final pressure. Okay, so determine the amount of work done on the gas. So work done basically is the formula that for me is quite complicated. So this will be our work done, which is 1 over 1 minus gamma. So P1 V1 minus P2 V2. Okay, as I said that if you are not able to remember this equation, so what we can do is actually derive step by steps. So in this case, I just directly write it down. So this is 1.40. So okay, my P1 will be, so okay, let me just find out this one. P2, so this is 1/3 V1. So what I can do is factorize this V1 into here. So this is P1 minus 1/3 P2. Is it correct? Yeah, it is. Okay, so 1 minus 1.40. So what will be my V1? My V1 basically is 3.5 times 10 to the power negative 3. So my P1 here is 1.013 times 10 to the power of 5 minus 1/3 the pressure of P2. So 4.716 times 10 to the power of 5. Okay. So 1 minus 1 over 1.40. So 3.5 times 10 to the power negative 3. So 1.013 times 10 to the power of 5 minus 1/3. 4.716 times 10 to the power of 5. So what we get is okay. So this one is okay, so there's a mistake here. So so the work done supposed to be negative. So okay. Alright. I wonder where is the mistakes here. So is it? Oh, I found it. And this one should be gamma minus 1. Oops. Wait. Wait, is it gamma minus 1? Yeah, is it? It is gamma minus 1. Okay, so this one should be gamma minus 1. I a bit forgotten about the formula. So for me, is the adiabatic equation is quite, the formula is quite complicated for me. So sometimes I will forget a bit. So this one should be 1.4 minus 1. Okay, so let me change the 1.4 minus 1. Alright, so this will be the final answer for us. 1 joule. So basically the work done is negative. So which the process is compression. Okay, so I think we have done for question 4. So let's just move on to our final question. So let me just erase all this one. Okay. Okay, so oops. So let's move on to our final question. So this is number 5. So a cylinder with adjustable piston contains 3.5 mole of diatomic gas initially at 0.125 meter cube and P1, which is 1.013 times 10 to the power of 5 Pascal. The volume is then increased adiabatically to 0.85 meter cube. Determine the initial and final temperature of the gas. So we have P, we have V. Basically, we can use the ideal gas equation, which is P1 V1 is equals to nR T1. So 1.013 times 10 to the power of 5, so 0.125. So what we have is, okay. So the mole is given. So what we have is 3.50. So the gas constant is 8.31. So my initial temperature will be 1.013 times 10 to the power of 5, 0.125 divided by 3.5, 8.31. So basically our initial temperature will be 435.4 Kelvin. So this is the initial. And what about final temperature? So final temperature, we have P, we have V. Basically we can do is P1 V1 gamma is equals to P2 V2 gamma. So we have V2, and the unknown that we need to find is P2. So this is 1.013 times 10 to the power of 5, and V1, what will be my V1? 0.125. So the gamma basically is F plus 2 over F. So since the gas is diatomic gas, so degree of freedom is 5, and this is 1.40. So 1.40 is equals to P2 V2 at 5, 1.40. So basically my P2 is 0.13 times 10 to the power of 5, 125 times 10 to the power of 1.40. So divided by 0.85 to the power of 1.40. So my second pressure is 6.920 times 10 to the power of 3. So this is Pascal. So okay. So this is P2. So back to the ideal gas equation, which is PV equals to nRT. So this is P2 V2 equals to nRT2. So what will be our P2? T2, sorry. So my V2 is 0.85 is equals to 3.5. So 8.31, and this is T2. So basically my T2 will be 0.85 divided by 3.5, 8.31. So what we get for temperature is actually 202 times 0.2. So this is Kelvin. Okay, so this is the initial temperature and final temperature. So let us move on to the final question. So this is change in internal energy of the gas. So change in internal energy of the gas, basically we can use this formula, nRT, delta T. So since the mole is given, so the formula for internal energy that we use is actually nR delta T. So this is 5 over 2, and this is 3.5. So this is 8.31, and this is T2 minus T1. So my T2 is 202.2 minus 435.4. So 3.5, 8.31, 202.2 minus 435.4. So what we get is negative 1.696 times 10 to the power of 4, and this is joule. So I can conclude that sorry, the process is actually adiabatic compression. So it is obviously, since the volume is expand from 0.125 meter cube to 0.85 meter cube. So this proves that the process is actually expansion. So since the process is adiabatic expansion, and hence the internal energy of the gas after the work is done, so the internal energy of the gas will decrease, and hence our temperature also decrease. Okay, so that's it for today revision of chapter of thermodynamics of gases. So the way that we do is actually a bit complicated, but if we are able to understand the concept, so we can do it slowly and do it one by one, so that we are able to answer it more clearly. Alright, so we have done for all these 5 questions, so I think we'll stop here now. So if there is any question need to be asked, and please comment below this video. So I'll see you in the next video. Okay, thank you. Bye.